All right. Hello, everyone. It's a pleasure to be here. My name is Stefano. Alva, and I'm the Director of Operations at Vitruvian. The session that we are about to start is called the Practical Applications of 3D Printing. This panel is designed to bridge the real-world deployment of 3D printing construction with academia and research. We believe that universities and research institutions are driving breakthroughs in materials and automation, but there's also companies in the field that are confronting practical barriers to scaling in the buckets of machinery, materials, and workforce. And so the goal of this panel is to align where research energy is being spent with where the industry truly needs innovation, ensuring that the academic progress translates to scalable construction outcomes. And so the overall question that we are using as a guidance for today is, what problems does the industry actually need to be solved today to move faster tomorrow? With that said, I want to first introduce the participants of this panel. Like I said, my name is Stefano. I'm going to be the moderator. My company is called Vitruvian. Vitruvian is in the process of constructing three 3D printed homes. We have built a state-accredited pre-apprenticeship program, certified by the state of Ohio. We have trained 27 high school students and 15 adults, which we have then employed in our construction projects. And we are using both concrete and composite 3D printing towards the housing and construction industry. We've also have some work that we've done with the Department of Defense. And so, with that said, is how I got to meet Jim Mantes. Jim Mantes works for ARA, and his application of 3D printing is focused on defense applications for the use of rapid infrastructure deployment. We also have Dr. Islam Montaway, who is a professor at Rowan University and is part of the Additive and Robotic Construction Laboratory. And I met him through the Additive Construction by Extrusion Consortium that is part of the NIST. And we also are joined by Jacob Henshin, who is a professor at University of Illinois Urbana-Champaign. And I connected with him through a 3D printing concrete working group where there's a lot of, let's say, like on-field concrete 3D printer operators and also some university, participation where we're trying to solve problems that the industry in 3D printing concrete is facing right now. And so the way that this panel is going to go is that each of us are going to give a brief introduction of ourselves and a brief presentation. And then from here, we're going to transition into questions that I have prepared towards the panelists. And the goal of us talking at the beginning is to spark questions, to spark doubts, to spark conversations, so that after, as I'm asking questions, you guys feel free to ask your own questions and be inquisitive about the experience that myself have had, but also the gentlemen that are joining us today. Sounds good? Fantastic. So I'll start with my presentation. Again, my company is called Vitruvian. We came to existence to solve two problems. The first one is, we believe, is the most important one, and it's the workforce problem. I'm sure that you guys are aware, but there's a shocking and worrying statistic that a lot of the construction workforce is a lot older than it was a lot of years ago. And so 40% of the construction workers are expected to retire in the next 10 years. For every 5 people that are leaving the trades, only 2 are coming in. There's 500,000 jobs in construction that are open right now. And so although this technology, 3D printing with concrete, has a lot of advantages when it comes to performance and efficiency, I think that one of the biggest advantages that it has is the ability to attract a new labor force. And so I am eager to share a little bit of how we are doing this and how we're showcasing this. And the other one is maybe more obvious, which is we need houses. There is a insufficient housing inventory. We are specifically focused in rural America. Our headquarters and our operations lie in Athens, Ohio, which is about an hour and a half south of Columbus. In this specific area, they're facing a very specific issue, which is OU, the university, every year is accepting more and more students. The city is actually growing, but over the last 3 years, there's only been 7 single-family home permits issued by the county. And so there is a decline of houses. All the houses that were built in the 1800s and early 1900s. And so every year there's more people, and every year the houses get in worse and worse state. And so rent is actually really expensive, especially to be a rural place that supposed to be more affordable than bigger cities. And so this is why we also have established ourselves in Athens specifically. So our goal as a company is to achieve community resilience, or to provide communities the ability to build for themselves. The idea is that we're solving these local problems using local resources and creating local opportunities with additive manufacturing. What does this really mean? It means that we have established a business in Athens that is employing people, providing jobs, is educating people on how to use these technologies, and then we are building together with the people and the machinery that we've brought in homes that are desperately needed. And the overall goal is to enable, again, these communities to build for themselves. And if a community can build for itself, then it can attract investment and it can attract local economic development. When an industry or let's say a big manufacturing plant is being decided where to be placed, the ability to place itself in an area that can provide housing for the people that are there makes that area a lot more interesting for investment. And so we truly think that by doing this on a homegrown fashion, and again attracting that local labor, we can make a dent in the housing industry and help these communities again be more resilient. So how do we operate? We have gone to this community, to Athens. We have educated the workforce there. We have taught them how to use these advanced robots. Then we are employing those people in our local construction projects. And after that, we are in the process now of transitioning and facing the community and in exploring how that we can better serve the community, whether it is with housing, whether it is with infrastructure. Our goal is to solve those local problems, again, and be able to tailor to those needs. So we have 2 robots that we have deployed. We have the Mantes, which is a large format composite printer, and we have the Scorpion, which is a large format concrete printer. So I'll be focusing mostly on the concrete printer and the work that we've done there. But just to give you an overview of what is the work that we're doing, on your left upper corner, see some of the furniture that we print with a large format composite printer. At the bottom there, we have the picture of the large format composite printer. On the right is some of the structures that can be built with our concrete 3D printer, alongside with a little sneak peek of what the machine looks like. And so, yeah. And so what is this need that I mentioned on the workforce side? I'm sure that this graph is, I feel like it's fairly popular. I always used to justify what is that we're doing. But again, there is 500,000 construction jobs open in the United States. And so as much as, again, we want the process to become more efficient, and as much as we want this technology to improve construction processes, I think that there is an intrinsic need for labor that this technology can address. And it's the idea that you go to a classroom of kids and you ask them, hey, you want to lay brick for 8 hours? Good luck with that, right? You show them a big robot and you ask them, hey, you want to play with robots and build homes? You get a completely different demographic. Kids that are digitally savvy, kids that are technically curious, that are intellectually, that feel that this type of technology kind of, let's say, like tickles their intellectual curiosity. And so I get very excited about the way that we have been able to attract, again, people that might not have been initially interested in construction, and now because of this technology find an interest in it. And so the type of training that we're doing, we are training high school students. We're also training existing labor groups. Specifically, we have a relationship with the bricklayers of Local 23. I'll explain a little bit about that. And we also work with transitional workforce. And so I'm going to talk a little bit about the partnership that we have with the bricklayers of Local 23. Local 23 is one of the locals that falls under the International Masonry Institute. So we have developed a pre-apprenticeship program that feeds into their registered apprenticeship program. So we did this work, again, in order to meet their recruiting needs. It's really funny that they share with us that at some point, years ago, being in the trades was a very sought out after kind of profession. A lot of times you couldn't just go and apply to be in the trades. You had to know someone that was in the trades, and you had to be referred, and that has completely flipped upside down. The people who in their opinion end up in the trades a lot of times are not the cream of the crop. They're people that are maybe not, let's say, going or shooting for very technically or challenging jobs, instead are looking for alternative education methods. And so I do think it's really interesting that we are using this technology to almost like get it closer to the people who are working with this material, with concrete, every day. So we are tackling 3 buckets of people that we're training. We're training new talent, or high school students to be specific, and attract them to the fields not only of construction, but manufacturing and engineering. We're also upskilling existing people in that local. So we have a group of bricklayers that participated in our training program that are regular, let's say like bricklayers that have been working as bricklayers for the past 5 to 15 years. And then we are also coordinating with supporting trades. And so we also give training to electrical roofers, plumbers that want to understand how this technology plays within their industry. So here, very graciously, we received earlier this year a Champions of Labor Award by the American Federation of Labor and Congress of Industrial Organizations. Long title. So this is a group of the kids that the people that we trained. Right here, we have kind of like this wide group, like I was sharing. The first 2 on the right are local builders and local contractors that actually do framing. And so they were not only helping us in our construction project by being part of our 3D printing, let's say, crew, but then we also employed them to do the framing of the 3D printed houses. Hannah is the next one. She's a bricklayer of Local 23. We have Seth, who's also a general builder, general contractor, who's also taking on other parts of the construction project. We have Tyler there, who is from a transitional workforce program. And then we have rest of the team is more Vitruvian, so our internal team, and all the way to the left is Eric, who's also part of the bricklayers. And we also do training for high school students. I don't know, just look at this picture. You never see kids this excited about being in construction, I feel. It's hard to see this type of excitement when you show them bricks, So I think that this picture kind of embodies this. It's almost like this feeling, except maybe this kid, I don't know, he doesn't seem too happy. What is this kind of chicken and the egg problem that's happening with the housing, and specifically in rural areas that I was mentioning? So local businesses say it's hard to find and keep workers because they are in good enough places for people to live nearby. Easy, right? The homes that exist are often old and in poor condition because, like I said, in Athens, there was a very few amount of homes that have been built over the last years, and the majority of the homes that were built was when Athens was a booming coal town. And so that industry has not been there for now, decades, which means that a lot of the local economic activity that used to happen because of that is not there anymore, which has left people not taking care of those houses. And then because many people in these areas don't have those jobs and have low incomes, it's difficult for them to afford or improve their housing. And so it creates this cycle, right? And the idea is that if we start and use this technology to address the issue at its core, we can kind of start breaking some of those, let's say, like patterns, and hopefully kind of reverse that trend. So what have we found in the homes that we've built, or why would you want a 3D printed house? We are building these homes, the walls at least, in a week. The homes have more flexibility on design, so you can argue that they're more aesthetic, right? This is a subjective thing, but you can see this is the floor plan of the house, so we got some curves there. Those are more durable than traditional stick-built homes. Concrete is a material that withstands flood, fire, and wind, and they're very energy efficient. So the space that there is between the inner and outer layer of the concrete wall can be adjusted to depend to the amount of insulation that is needed. And so, if you want R21 and you're using spray foam, you leave 4 inches or 3 inches of space, so you can get your your R21 value. If you need more because you're, in Alaska, you might leave more of a gap because you need R40. Right, so being able to adjust to that need of insulation is something that 3D printing can do quite versatile. And then we're excited to start building with local and recycled materials. And so a lot of the panelists here that are participating have had the opportunity to develop their own materials or work with local and native materials and indigenous materials. I'm very excited to learn about them, and I'm very excited to integrate kind of these practices into our own. Sharing, this is the floor plan of the house that we built. We're building 3 of those. I'm going to start showing some pictures and kind of just walking you guys through the process. This is what 3D printing looks like. So this is a video of us actually testing one of the walls that was going to go on the floor plan. Here is a lot of the trainees. Kind of, it's really funny. We brought Hannah, which is one of the bricklayers. Was very skeptical about joining the training because she was worried that robots were gonna replace workers or some sort of kind of like this type of narrative that sometimes tends to be common. And she was delighted to find that that the work is a lot less laborious. It's a lot less work intensive, and was able, and like what she felt is that she could actually work more because she's not literally carrying bricks 8 hours a day. And so I think that that's one of the stories that to me kind of took my attention.
Yeah. So we're playing with, instead of doing a column like that, we just basically use this horizontal thing, and we place one here and another one here, and put one here and then another one.
So that's me explaining actually how we thought about. We did some testing, and I wanted to explain a little bit of the testing that we were doing. On the left picture, you can see how we are using the 3D printer to create a partition within the wall. And the partition would allow us to fill in one section of the wall with concrete and another section with insulation. And so we were experimenting if we could get rid of this partition. We don't particularly like the aesthetic look of the partition. I'm going to share a couple pictures of how it looked. And so instead, this video showing is the way that we ended up addressing that specific challenge. And so I'll share here the next picture. This is not an amazing picture, but I wanted to kind of zoom in right here. What you guys are seeing right here is two pieces of ladder wire that are spaced out about 2 inches in distance, and we space these out throughout the wall, like in a vertical fashion, so that then we can place a wooden board in that specific cavity and create, let's say, like an artificial gap between where we want to place the concrete and where we want to place the insulation. And so this picture shows here kind of like what that wall would have looked like if we would have left that partition in there. And we're just not big fans. Our clients were not a big fan of this, so this is a way that we innovated out of it. Our clients claimed that they look like a rear end, and so we were trying to figure out a way to not use that. After kind of this testing process, those were not the only things that we were testing for, but there were things like this that we were figuring out prior to the construction process. Loading everything, we were able to load everything that is needed to print in 2 trailers, one open trailer, which takes the silo, water, our generators, and some other auxiliary equipment. And then in an enclosed trailer, we're able to fit our printer, our pump, and then let's say like the electronic and more like sensitive equipment. And so with these 2 trailers, with an enclosed one that is similar of this size and an open one, we can go to site. We then also plan for the positions of the machine. And so here we have how the house is laid out. What you guys are seeing here is this machine is actually this placement. It seems to be a little bit to the right of the center. And the reason is because there was like plumbing coming from the concrete foundation because it was roughed in, it was sticking out. And so we kind of had to shift around the placement of the robot so that we can not be on top of that, let's say, plumbing roughing. And so here is the position of that machine and how we kind of had to go around the plumbing and get really close to it so that we can print the entire area that we wanted to print from the same position. So I just want to run through some additional pictures. Here we have us building. I think that there's a fast forward of one of these. Excuse the shirtless people. Where it gets hot on site. So every 12 layers, at the beginning, we place ladder wire somewhat periodically, but after the first feet, we place horizontal ladder wire across the structure to serve as a tie-in between the external and the internal layer, and then we kind of like patching the layers, trying to make it look as good as we can. This is the proverbial nice looking bead being extruded. I'll let you guys enjoy that for a second. And then I want to share, like, again, some little nuggets here of information. So this contraption that is here is a pallet with a composite 3D printed funnel on top. And so the reason why we printed this funnel is because the material that we were using, it seems to have been sitting in a warehouse for a long time. I don't know how long it took us, how long it was sitting in a warehouse from the moment that it was made until it arrived to us, but it was very compacted. And because of this, we were having issues. Even when we opened the bottom of the silo bag of the bag, so that it goes into the funnel, the material wouldn't be flowing. And so we had to create this contraption for the corners of the bag to basically hit against the bag. Sorry, the corners of the bag to be hit with this wooden, let's say like 4x4s, and then for a funnel that could allow the material to sieve through. So this was literally on the fly. We were mid-printing. We saw that the bags didn't flow well. We went back to our shop. We printed this funnel with our large format composite printer. We put it in. It worked. Kept going. We think that we're going to be moving towards some sort of combination of system that completely eliminates the need for a forklift to load bags. And so instead of having a silo, we see ourselves transferring to a system where our pump, which I'm going to go back, is this that you're looking at right here, is fed directly with a conveyor screw like this one. And this way, we don't need a forklift for the material to be raised so high, because with a semi-electric forklift, there's actually manual versions of this. We can lift the 1-ton super sack just to this distance so that the material can then kind of flow through. And so this is the direction where a lot of our engineering efforts are going into. And by eliminating the need of a silo and a telehandler, we are effectively, and a forklift operator as well, we're effectively eliminating something like $500 a day of operations. And so among like the prioritizations of where we want to put our efforts and energy, this definitely makes a difference. We also did some on-the-fly design changes. So we had a specific wall that we were printing. It was this one that after printing the first house, we figured that it was actually, it was like overkill. There was too many windows, around here. There was French doors here that were letting a lot of light out, and there was a lot of a light from here because we had a skylight. And so this specific window required us to basically have an additional day of printing. And so we changed that design and eliminated that wall and just did it all at once. And so that's a very, I would say, like a very neat thing that this technology allows us to do, to take the digital file, make changes on the fly, and be able to modify the construction project kind of like without, let's say, like major headaches. So now I want to talk a little bit about the integration of this, let's say, like our builds to traditional construction. So you use J-bolts for framing, which basically is how the wooden studs went against the concrete 3D printed walls. We then use J-bolts as well for the bond beam. And so on top of this bond beam is where we grout it. And so we have vertical columns on each side of the wall, or, if the wall is really long, we had a vertical column in the middle. And then we grouted the bond beam up top so that the top plates can sit on top. And after the top plates are on top, you're basically looking like at any other roofing solution. I mean, that's something that the carpenters can run with. I also want to talk about cost. So these are very general numbers, but roughly what we were spending in the 3D printing operation was about $36,000 per house, which contributed to roughly $26 per square foot to the house. This was our first time building a house, and so we ended up spending roughly $282 per square foot of total build cost. This includes everything: finishes, furniture, like absolutely everything. A turnkey house. This ends up, I would say in the range of cheap to expensive. It's on the expensive-er side. It's still not, completely out of the norm that this is something that of what a house costs. There's significant work to be done to reduce these costs, and I'm excited to talk about some of those costs in this presentation. And just kind of complement with some other things here and there. So we used a composite 3D printer to do furniture. So for example, we're placing these rocking chairs in the house inside, which is another neat thing how we're integrating these two technologies. This is a little bit of our traction. So we have our two printers in deployment. We work with Department of Defense on kind of like using their IP and being able to leverage it towards our needs. We're building 3 homes through 2025. We have the state-approved pre-apprenticeship program. We have trained 17 adults to date and 27 high school students that are enrolled at the moment. They're going to be graduating from the pre-apprenticeship at the end of the year. And that is the end of my presentation. I appreciate you guys listening too. I'm going to be inviting some other gentlemen here, specifically Jim first, for him to run through some of the work that he's done before we get to questions. So thank you.
Mine's a little bit shorter than Stefano here, but Acme Tech. So I'm Jim Mantes. Work for a company called Applied Research Associates, ARA. We're headquartered in New Mexico, but have offices in 30 states, about 3,000 employees or so. So we mostly focus on the defense community. Most of what I'm going to talk about today is applications of concrete 3D printing for specifically the Army. And we'll get into kind of some of the nuance of the research we did. But the charge was, what if we go to an austere location? Construction typically has a large logistical burden. How can we use what we have on the site to make concrete structures? So really the charge was to use site soils mixed with cement, maybe additives, and make concrete out of it. How quick can we do that? Can we do that? How quick can we do that? What do we have to bring with us in order to do that? And what kind of training would be required to show people how to do that? So if I can, we'll see if this will work. It's a good video that kind of summarizes what we got. Yeah, so that kind of primes this up a little bit. The Army came to us and they said, we need a system that we can deploy, anywhere in the world, fits inside of a plane, it can get slung low under a helicopter, it can set up quickly, It's compatible with pretty much any other shipping mechanism we have. You kind of saw it riding around in the back of that truck they call their palletized loading system. And then, oh, by the way, we want to do infrastructure elements, right? Not a whole lot of that going on right now. A lot of it's lower load case, buildings, and things like that. You know, so right away, hey, we want to cross tanks over culverts and bridges and what have you, right? So we want to go up to our biggest load case, 150 ton MLC 150 load case, right? And then, oh, by the way, we want to use site soils. We don't care if there's silt in it. We don't care what you have. Figure out how to print it, right? So we worked that problem. We worked on a slicer solution for them, for those familiar with 3D printing. Can we get a show of hands on who's into kind of concrete 3D printing in here? Okay, so some. And then people that are at least familiar with the concepts and ideas behind it. Okay, good. Most people, good. All right, so not talking too crazy here yet. So yeah, doing it with indigenous soils, and the big reason for them was reducing logistical burden, right? Instead of shipping, you know, cement and sand and rocks and additives and all this stuff from here in the US to wherever they want to use it, how can we bring that number of stuff we need to ship down, right? Just bring what we need, whether that's just cement and additives or whatever else, right? So that was kind of the charge. We developed a slicer solution for them as well that we'll walk through a couple of the high points. And the main thing here is just to kind of spark some questions in your head for later when we get into the panel piece. But bottom line is turning indigenous soil, stuff we dig out of the ground, out of a riverbed, off of a hillside or whatever, into power projection, right? What the military calls moving things, people, down lines of communication, routes, roads, etc. So here's kind of our general setup. Printer shown on the left. You saw it kind of in the video. We've used the Army's portable concrete mixer shown kind of in the center. We've got a prototype piston pump, dual piston pump that we're using for our solution that's been working for us well. And then the material handling equipment. Pretty agnostic, telehandlers, skid loaders, that kind of thing. Oh, I thought I closed that. I think that's outside. Radio traffic, sorry. Yeah. Okay, so last touch point we did was in September. So just a couple months ago, we were up at Fort McCoy in Wisconsin, doing some work with some soldiers from the Wisconsin and actually Maryland National Guard were out there with us. We trained 7 soldiers on how to do material characterization and site identification of soils. So we dug up soil from the site. We characterized that. We processed it with some processing attachments that I'll show in a minute, went through the mix design process, and then ultimately printed with it on site. So here's just showing printing some of the culverts from that video, and here's just kind of that assembled, you know, component. Mind you, most of what we're doing here is for what we call contingent construction, so think temporary, right? This isn't 75-year design life stuff, typical that we'd find in the US. This is year, 2 years, something that you need to do to get the mission done, right? Next one, this is going back a couple months to right after Memorial Day at Fort Hood. We helped them construct a bunch of these objects here they call dragon's teeth. So they're tank obstacles. You lay them on the ground in arrays and they help stop tracked vehicles from moving when you pair them up with wire and ditches and other things like that. So down at Fort Hood, they're building a large complex obstacle belt. So we went down there to kind of show off the AC technology as well as help them build that obstacle belt. Here's them just showing carrying one of these off and kind of how they can be moved. They can be printed in place or moved. That's the way they were designed. This one's actually going off to a demolition range to do some explosive testing on it. As part of the project, we came up with like a catalog of some various things that they could make. These are like pre-engineered designs in a variety of sizes. They're into strength bins, 1 KSI, 2 KSI, 3 KSI concrete. So you pick your material strength and the size of the object. It comes out with the file. Well, we've got a couple of things shown here. Some box culverts, dragon's teeth, T-wall, jersey barriers, stackable blocks, short gap crossing segments, and some round culvert pipes. Here's what some of those things look like as assemblies. So top left, you know, short gap crossing, that's 5 meters, 15 feet or so. Gap crossing, those are, you know, concrete segments that were printed. We did a small cast and place deck on there just for fun to use up some material. And then the bottom piece is their post-tension, 1 3/8 post-tension rods. top one in the right, just a spattering of different stuff that we printed and put together. Then in the bottom, you see the round, and then on the bottom right, the square box culvert kind of assemblies. So you can imagine how that goes. So as part of the process, like I mentioned before, you were using site materials, right? So top left, dug out of a site. We're using crushers and screening attachments that go on a skid loader. It's interesting they keep up. You know, it was kind of one of those researchy areas where it's like, let's see what we can do with bringing the minimal amount of stuff. And you can keep up with your printing. If you get about a 2-hour head start, you can keep processing material out ahead of you. So it works pretty well. Bottom right's kind of the end product of what goes through from that pile in the top left to the bottom right. So you've got fines in there, you've got gravel in there, coarse aggregate, you've got fine aggregate sands in there, and also, you know, silt and clay fines to a percentage depending on what's in the original soil, right? The screen that we're running on there is a 1/2 inch. So typically we're using 1/2 inch minus nominal aggregate size. This one just shows a little bit about some of the characterization process and some of the tools we use. So the Army has what they call a rapid soils analysis kit. It's comes in some big hard Pelican cases full of stuff, sieves, spatulas, a microwave for drying, bowls, different things, right? Different soil analysis tools. So we use their kit in a little bit different way to characterize soils for making concrete. A couple things that we added to it, the KitchenAid mixer. That's how we do some small batch mixing on the site just to test the mix out, see if it's going to work before we load it into the bottom right, the portable concrete mixer. This is just showing a picture of some of our soldiers rolling through slicing. This is the looks of the slicer program that we wrote for them, and some of the items that are in that catalog. We've since added another 5 or 6 things, but you saw the pictures of them printed already, and this is just what that UI looks like from the slicer software. Just another photo from the Fort McCoy experience. Again, kind of walking back, the uniqueness here, the printer's unique. The portable concrete mixer is something the Army already owns, so they were interested in us using that. And the major difference there is we're site mixing, right? Because we're using soils from the site. They've got a moisture content. They've got fines and other contaminants in them. So it's a little bit different than some of the things that you hear from others with dried out mixes, pre-bagged, running my pumps, running MTUC dual mix pumps, different things like that. All great things. We have all those things in our lab as well. We started using them, but that's not where the Army wanted to go, and that was the necessity for really the key component on here of that dual piston pump. So we've made some pretty good headway into figuring out how to do that and how to eliminate some of the pulsation of flow that comes along with that we can chat about a little bit later in Q&A if people are interested. Ask a question, and I'll talk a little bit about that. But that's kind of the most unique thing on here is probably that dual piston pump. Here's just a photo of the group from our last experience earlier on that week. Here's another photo. You kind of saw it in the video, but just a photo of some of the stuff, the gear loaded up on the back of the PLS. That was one of the requirements for the project. Testing. So we have done some testing with these concretes. We've done about 60 different mixes from soils from all over the world, which I'll show in the next one. But this is, FEA versus actual testing on just a beam specimen. We've also done culverts and a couple other different objects. But generally, we're falling between like 6 to 10% variance when you're using a material model that's tuned to the material, and when using a standard KNC damage model and LS Dyna are getting somewhere between like 11 and 15% different. So you're not gaining a whole lot of percent confidence or percent match by running a lot of analysis on it. It's actually the generic models within Dyna are pretty good as long as you've modeled the structure appropriately. As far as materials go, like I said, the Army was interested in using this, anywhere they want to operate. So we pulled outside of the continental U.S. material samples from locations shown on here. Most of them we pulled multiple samples. Every sample that we pulled is 5 to 10 5-gallon buckets for the most part. So enough to print something small with and characterize and all that, but not mass quantity to build something huge. The idea was to pull in materials that we could find a somewhat surrogate for, more CONUS based here in the US. So that was kind of the thought process behind that. And that's a bit of what I have to kind of prime this up and intro us. So again, Jim Mantes with ARA. We're working this project with U.S. Army ERDIC, Engineer Research and Development Center. We've got partners with University of Arkansas and Iowa State and Robotic Construction Technologies on this project. Thanks.
Okay, thank you for tuning in. So my name is Islam Mantawi. I'm an assistant professor at Rowan University. Our lab is called Additive and Robotic Construction Laboratory, ARC Lab. We work on both concrete 3D printing, and we also 3D print metals, both for infrastructure and buildings. In 3D printing of concrete, we are doing topology optimization. We work on systems that can resist hazards like earthquake, fires, and extreme winds. We develop our own material locally sourced, not at the site, but near site. We examine different reinforcement technique. We are focusing on inline reinforcement and also multifunctional structure. In the metal side, we do the similar research, but we focus on also repair using cold spray and meta materials. So I usually start my presentation with this slide showing the difference between construction in general of concrete structures from 1950 and 21st century. And I always ask, what's the difference? And if you have any answer rather than black and white, it's a wrong answer. So it's the same thing we do over years. The reason, because we build large structures. We are not building small elements that's, you can iterate and improve. You are in a scale of meters and feet, sometimes in bridges, in even miles. So we need production and efficiency. So we categorize construction in our laboratory to 3 different groups. The first one we call it conventional construction, when you have forming, placing, reinforcement, and casting. We call most of the additive construction technique hybrid construction because you use mainly printing formwork, placing, reinforcement, and casting. So you still need post-process technology to finish the structure. In our lab, we thought of inline or in-process integration so that once you finish the print, you have your structure ready. That could be by optimizing compression-only structures or developing structure that actually work nicely with inline process of reinforcement. So back to the materials, as I mentioned, we are developing our materials. It's New Jersey, South Jersey, near Philadelphia. So we are almost sourcing all our materials within 20 miles from the university. We do the basic testing to reach to a viable mix, from flow table to setting time to testing linear material a lot with the printer itself for extrudability and printability requirement. And on the right side here, we have our flow chart showing that we have like a scaffold approach to, since we give me the aggregates and binders, we are stacking it in this approach to actually improve and qualify the material for printing. So the printer we have is a commercial printer from 3D Potter. It's a robotic arm mounted on a 14 feet long rail. Can print 360, so it can actually enclose itself with like a dome type structure. In one setup, you can print 20 feet by 7 feet by 7 feet. And here, the print speed, and as I mentioned, 360. Like whole circle print. We have two or three systems we're going to show later. One is closed system when you have a tube, and this is mainly for material development and smaller structures. And large one that has the auger system and the full pumping system. So to show here is our 3 systems that we have side by side, starting with a smaller tube to extrude material, to then open auger to feed the material to the auger and extrude, and also the open system where you have the pump extrude the material just to end of the hose nozzle. And the same material is actually printed from all the 3 systems with a little bit tweaks on the rheology. But as you can see here, we are on the left side printing down to 5 millimeter nozzle to half-inch nozzle to 1-inch nozzle. And we are not using Excellent in like 95% of our mixes. we are actually achieving the slopes without any accident, either in the mix or at the nozzle level. We also examine or develop mixes that incorporate steel fibers. So those are smaller steel fibers that 6 millimeter, 4.5, and 13 millimeter. In some mixes, we were able to get to 1% by volume. And you can see here the material is extruded with fiber within it, and you can see the quality of the material is a little bit compromised because of fiber well alignment, etc. You can see on the interfaces some porosity. As part of our material performance testing we actually try to print on the slopes. So this is a 26-degree slope from a vertical position. We printed a pyramid that 12 inch by 12 inch by 12 inch, and the material here using steel fibers. We also were able to print it without steel fibers. This actually sparked an idea for us, like, want to see without accelerant how much slope can I retain? So we came up with different design that is like flare design. You can see on the left side a nice early version of it with fiber, on the right side without fiber. And we actually print and stress test the material to see where is the weak point and when you're gonna fail. On the left side, you can see you start losing the seat, and material is extruding in the air, a little bit problem here around the left side, and almost partial collapse that actually define for us what could be the slope from vertical position. As a conclusion, we have really nice 45-degree slopes on material and non-fibrous mixes, while if you add fibers, we are able to bump that to even 65% from the vertical position. That could be useful for some practical application, what we call it segmental printing, where you can print back and forth 2 piers or a gated structure or arch structure, and after that joining them with top slab. So we did that last year where we fed the material to the auger. We printed 2 side piers, left and right. This was our first iteration of this structure. We never tried before. It was the first time. We take really high pride of the quality of the materials. I know that we discussed that, Jim, earlier, that your quality is based on the target performance, and you are working for Army and application that is short term, but for houses, we need higher quality, so we focus a lot on the quality for houses. We have a project that we actually try to use segmental 3D printed columns and post-tension to create columns for seismic application that allow the column to rock back and forth, and using supplementary system to damp the forces. So you can see here at the end of the column, we were able to flare the column and create like a elbow joint or a knee joint where you have a socket and ball connection. And within this cavity, you can have damping material that can dampen the force as you rock. We also can attach external element that dissipate by rotational friction. We also can print segmentally and connect them with post-tensioning. And you can see here on the right side, we have like cavity for post-tension and cavity for rebar to grouted in process. As I mentioned, you also work on compression-only structure, where it's designed actually to maximize compression forces, minimize tension. We didn't reinvent arches, but with 3D printing, we can come up with really nice design for arches that we did at Rowan, and the right side actually using LiDAR to scan and compare it to the original file. We do research for 2 years now on underwater 3D printing. We actually develop material so that we can print concrete underwater, and you can see here, this is one of our least attempts, and we were able to almost have 0 washout on those mixes, and the speed of the video is like maybe 2 times, but this gives you an idea that there's a lot of challenges for underwater 3D printing, especially if you want to, upgrade reefs or, caissons underwater or repair of bridge columns underwater. So we have this research for almost effectively 1 year, but we started this idea like 2 years ago. So we also do a project on shelters. So this is actually was because we, for a long time, used the tube, which is a hassle because you have to stop, refill, etc. So we thought about printing brick type units that can be printed at a scale and using robotic arm to assemble them, put the foam for insulation, put battery power lighting, etc., and also leave opening for windows and etc. And idea is to have 2 people to assemble those shelter quickly on site, especially for pre and post hazard preparedness. So one thing I want to pick your mind on is we really lag as a concrete 3D printing behind a lot of other technology that like metal 3D printing or polymer. If you're familiar with PLA or polymer printing, you just have your 3D slicer, turn on the printer, leave, next day you have the print done. However, as you see from the videos before, presentation before, and also the one on the left here, that we have to have interaction between the worker and the printer. And that could have some safety situation and also very subjective because my judgment on the quality will be different based on the situation. And this is actually, if you want to scale it to metal 3D printing, is like putting a labor inside the 3D printed metal with sintering up to 1500 degrees Celsius. So we need to have really, I know Raksh here is doing a lot of good work on in-process monitoring of bond between the layer. So a lot of work needs to be done in in-process monitoring. And this is comparison between metal and concrete. As opportunity, we know the concrete is much stronger than wood. So in wildfire, the worst 3D printed home will perform much better than any of the wood construction. I was in Los Angeles last couple of weeks, and you go to Malibu Beach and see most of the structure that was damaged was due to the wood construction. So I think once we master this technology and have those houses, there's going to be a lot of benefit for fire resistance. For hurricane, this is a concrete structure that was elevated in Mexico Beach for one of the hurricane, and this was only the 2 houses that was surviving. A lot of research on flooding, especially the quality of the interface layers and seeping the water inside. There is also research in seismic, as I mentioned to you. A lot of work that can be done in seismic for coastline protection and artificial reefs using 3D printed artificial reefs, and also for hazard preparation, where you can actually, usually what we do now is like large scale evacuation in large facilities. We were lucky during COVID that we did not have hurricane and conflicting requirement of social distancing. So we thought about like smaller shelters, units that can be assembled and provide privacy and social distancing. With that, I would like to thank you, and I look forward to the discussion later. So thank you.
All right, thank you very much. I promise I will keep this as short as possible. So my name is Jacob Hench, and I'm a teaching professor at University of Illinois. And so I'm a little bit of an oddball because I am not primarily responsible for research. And so about 10 years ago, I was talking with a colleague at another school, and I was like, man, those 3D printers are pretty cool. What do you think about me throwing some concrete in it? And he didn't chase me out of his lab, so that's kind of where my interest in this was born. And so as this work has evolved, we got involved in a 3D printed concrete company called LX Construction. And so if you're interested, there's the website. They have an Instagram presence, a LinkedIn presence, and they have a lot of really cool videos that kind of show the development that they've had over the last several years. And I'm going to talk a little bit more about the history with this kind of partnership in a little bit, but again, I'm going to kind of start from the beginning. Right away when I started doing this work, I realized that this idea of concrete rheology was so incredibly important. I've been doing rheology even back in my graduate program. And so when we started to think about, okay, we got to get a material that can actually be extruded, but then retain its shape, this is not an easy topic. In my graduate program, I had a rheometer, and this is great, but boy, that thing was sensitive. This is not a field-ready device. And so when we start to think about that, well, none of the rheometers are really field-ready devices. And so I really wanted to start thinking about alternatives to how do we measure and kind of work with this rheology. And so I started really, really simple. So I just started with a power meter on a mixer. And if you keep that volume consistent, then we were all of a sudden able to start to differentiate mixes in terms of how easy the mixer was processing it. This also started to correlate with some of our early extrusion tests, which all of those were more just visual. We didn't actually have any data on that. And so that got us thinking, okay, so we can be a little bit more creative. One of my other research projects was looking at formwork pressure for highly flowable mixes. Okay, and so if you are familiar at all with formwork design, okay, so the lateral pressure that concrete exerts on that formwork can be a really big problem. And so I worked with modeling that, and that made me think of, well, isn't that building up of the structure and the decrease in the formwork pressure kind of the same thing we want to do with our 3D printed mixes? And so then I kind of pulled out the old playbook and started looking at lateral pressure as a way to characterize the thixotropy, the buildup of these printable mixes. And so kind of combining these two, we started to jump into this and gain some headway to actually get stuff to extrude through our printer. So jumping forward then a couple of years, I changed institutions, started working with a research faculty a little bit closer, and then we were approached by LX Construction, and they came to us saying, okay, so we just bought a concrete printer, we bought a volumetric mixer, we bought a pump, we bought all these materials. Now, tell us about concrete. They really didn't have a lot of background in concrete or construction, or 3D printing, or a lot of the things that you would think would be necessary before you jump into this. But they were willing to learn. They were really open in terms of, okay, we need this. Can you work with us here? And anything we did, they're like, yeah, please publish it. And that was something that was really appealing to us, that we would actually lend our expertise and really start this partnership. Now, they did give us some requirements. They did not want to do pre-bagged mixes. Why? Because they wanted to just be able to go anywhere locally, grab materials, and get to work mixing, placing, or printing, and be able to not have to do 20 trial batches every time something changed. The other thing they told us is, well, no admixtures. So they didn't want us to come with workability modifiers. They wanted to just be able to keep it really nice and simple. We are able to use Aaron trainers, but the rest of the stuff, they wanted it as simple as possible. A coarse aggregate, a fine aggregate, cement, water. So that presents a lot of problems, because they also wanted us to be able to pump this and then have the properties that we need to actually print and hold shape. And so Ben worked with us for the last couple of years, helping them and working with them to develop these things. And then this is some of the stuff that's come out of the work. The white structure that actually, I think that's you, Ben, standing next to, it was their second attempt at this, and this was a garage for the owner. And even though it looks a little bit like brickwork, they actually just were following the printer and striking little brick marks, which was kind of clever because it certainly made it look a little bit nicer. But then the bottom picture is they did a lot of proof of concept testing in their enclosed facility. They were working with this draft angle too to see if they at one point said, let's try printing the roof as well as the walls. And they actually, I think they could probably get it if they worked at it a little bit more, which would be kind of interesting. So as this development has gone on, they've really tried to continue to push the limits of what this material can do. So a lot of printing companies that you see, they're doing, maybe 3/4 of an inch to 1 inch layer heights. And Nathan was not satisfied with that. And so you can kind of tell from these pictures, these are not 1 inch layer heights. These are a little over 3 inch layer heights. So these are about 3 by 3 inch sections. They really worked hard to make them look nice, because if they are going to start printing homes, they want to be able, people have to like the look of the house before they move in. So they wanted to look nice, but then they also wanted these taller layer heights so that way printing time can be cut down. Their goal would be to print something like this in about a week. This was about a 2,000 square foot garage where the printer they have is a Cobod, so it's a gantry style, sits on the outside, sits on the perimeter of that, and they would be able to basically print continuously. And with this structure, I think it was about a 20-minute layer time. So, and that's just because that's how long it took the printer head to do the full perimeter of the structure. So that led us to have to work very hard to come up with, how do we deal with no admixtures? How do we help them get to the rheological properties that they need to get to? And so this is a lot of Ben's work. So this idea of working with a mix where you think of the aggregate system as, these solid particles, and then the cement is coating those particles, and that's the film. And so the thicker the film, that's what's going to ultimately start to really change your workability. So if it's too thin, it becomes unworkable. If it's too thick, all of a sudden you get bleeding, you get segregation, things like that. And yes, we acknowledge then that film, it has its own rheological properties. So if you go to high water cement ratio versus low water cement ratio, that's going to change how this film interacts within the whole system. So the question becomes, what is the right test to do? And so there we go. There's all the pictures. So I mentioned that, started with some really simple kind of very rough tests. Then we started to say, okay, let's bring the rheometers back in. And so Ben was very diligent, starting with just the regular ICAR rheometer, then moving to this interface rheometer with now instead of having the vanes, now you're looking at the interface and the lubrication layer that's formed. Then Ben got really involved in building, and so then we got a extrusion rheometer, which so now we're measuring the force that it takes to extrude the material through an orifice. And last but not least, then we also really started to look into basically the susceptibility these mixes had to bleeding. And so with all of that in mind, then we also threw in this field vane test, which actually Nathan found that one for us because, hey, this is something that they could just run while they were printing and kind of keep an eye on the change in kind of yield stress within their mixes. Okay, and so Ben really threw the kitchen sink at this to try to characterize everything. And so, what were the key findings? Well, it all boils down to water cement ratio. Really has a big effect on the bleeding. So if you get too low, you reduce the bleeding. If you get too high, you get more bleeding. And what we've seen time and time again with many of these tests, it's been confirmed out in the field too, is if these mixes are allowed to start bleeding, all of a sudden you start to pack the material, and that's when you start clogging pumps. That's when the extrusion head no longer wants to do its job. I've unofficially confirmed this so I actually teach a unit now in my concrete class on 3D printing where the students have to develop their own mixes. And every time we get a group that their mix bleeds excessively, I can tell them right at the beginning that, hey, that's going to extrude for the first, several hundred milliliters worth of material, and then it's going to jam and clog, and that's inevitably what happens, okay? And so then Ben broke it down to this idea of looking at the fine particles to the total sand, and then total sand to the total aggregate ratios, and how they start to affect pumping pressures, bleeding, all these things that we're using to try to get to an answer of, okay, what is the best way to approach these mixes for a 3D printing field type application? And so this work is going to be continuing on with a new student because Ben graduated and decided to join the real world. And so we are, like I said, we're going to keep this going. Now, we aren't just doing the rheology. We're also have the opportunity, we're doing some full-scale testing now too. The great thing about our facility is, well, we can go full size. So right now in our lab, we have 14-foot by 10-foot wall sections that were brought in. And yeah, we're in the process of testing them. The really cool thing about this is they told us about 29 kips in it as a compressive load to expect. And actually, this isn't even accurate because this test was completed on Friday, and they hit 110 kips with this wall section. And so, with all that said, we have a whole bunch more testing and work to do. And yeah, so that's where we're at.
Appreciate everyone that shared their respective findings and their work. I mean, it's impressive. I'm super honored that all of you agreed to be on this panel today. Now we're going to go into the discussion section. I have some things that I want to talk about. I have some things that I particularly want to learn from these gentlemen. But at any point in time, please feel free to raise your hand, go to the mic, ask a question. I'll be moderating the panel, and I'll be asking, giving a little bit of a background before I delve directly into the question. But the topics that we'll be going through is going to be printers, pumps, and material. And maybe if we have time to do a little bit, I feel like we're all very passionate about what we're talking, so we lasted a little longer than expected. So if we get time, we'll get on the workforce side. But let's start with printers. So in the early days of concrete 3D printing, gantry style systems were the standard. Over time, we saw the introduction of 6-axis robotic arms, which provided higher precision and were ideal for more intricate and architectural or interior design components. And now we have expeditionary systems like ARAs, Acme Tech, our system, the Scorpion, and others, which are built for mobility and rapid on-site deployment, which to me leads to the conclusion that the field is not moving towards one universal machine, but we have a diverse ecosystem where each type of machine has found its niche. And so the first question that I have, and please feel free to answer, is that are we truly phasing out gantry style systems, or there is still a place for them? And I want to highlight Jacob's experience with a LX Construction that they are using a gantry style systems, and they seem to be doing all right. So I'd love to get your guys' thoughts.
Yeah, I can start with that. So our the system that we put together for the Army was pretty unique, right? It had a unique use case. It needed to transport a certain way, needed to fold up, needed to do all this. And they were specifically at the time not interested in the robotic arm type, mostly because of field maintenance. How do we fix it if it breaks and we're somewhere where it's hard to get parts? Most of the gantries, at least the one that we put together for them and others that they put together over time, are driven by belts or chains and motors that are pretty easily be replaced with like 4 bolts. You can keep a spare on hand. They're not very large. So the maintainability and operations part was the main reason that we went that direction. So if you don't have those same challenges, there may be some other input on the robotics end of that.
Interesting point.
So I think the main driver for LX kind of going with the big gantry was, well, one, availability, because they started this years ago when some of the other systems were not as common. But the other advantage with the gantry system that just kind of encapsulates your entire work area is you don't have to sit there and continuously reset it and resurvey it to locate it. If you can only do half the house at a time, then you have a very clearly defined separation. Nathan is also, he comes up with some great ideas. He's even looked into using this gantry style printer to do the slab work and the flat work where, very simply just attaching a trowel to the printer head to very accurately flatten a slab, which again, is just going to speed up construction. And when you want a house with a nice flat floor, I don't know how much more accurate you can get than going with a system like that. So I think it's absolutely kind of different applications for the different technologies, where trying to go for a house type system, you want it to look nice. And so you want to be careful about how the layers look and where they're positioned and things like that. And so at least for now, the gantry style system has worked out very, very well for this particular application.
I like that. On one point there, Jim, I would say that the way that I interpreted your answer there was that it's almost like dumb printers or without the bells and whistles. They may not have these nice features that Jacob maybe like highlighted, or the ability for the like the prints to look really nice, and maybe they lack certain functions. And again, like bells and whistles, I feel like it's a nice word to use, because if you don't have the bells and whistles, there's literally less things that can break. And that ultimately ends up being an advantage if you are in an expeditionary environment. But if you're in a residential, you want the bells and whistles. You want to be able to accurately and precisely monitor how each layer is looking, which aesthetics might not be the priority in an expeditionary environment.
Yeah, that is a good point. So we have added like LiDAR to do some monitoring and some other things to it, but it can function without those things. It can go all the way back to just touching the nozzle off on the ground to set 0 versus using LiDAR to do that for us, or different touch probes that we've experimented with and tried out. So all those things that we added to the printer are like maybe help the soldier reduce cognitive load on the job site, but if they break, you're still operational.
One thing to add about the gantry system is, like, when you aim to print community of houses, is the setup is also time consuming. So let's say, so for example, the gantry system that you have, I don't know which one you have, but it requires casting foundation to hold the gantry. Which one you are using?
So it's the Cobod printer, and it takes 6 or 8 concrete blocks that get set in about a day that are movable. And it takes about a day to set up and a day to tear down the whole printer.
Yeah, that's pretty good. I mean, and to that point, I would say, like our system, for example, we are out of the shipping container and printing with like about like an hour and a half, but our footprint is also a lot smaller, right? And so now you're trading off, like if you can build, like and I think the Cobot 2.5 has a print volume of like 2,400 square feet. And so if you are focusing on big houses and you can only set up once and basically print or even 2 floors with one single position, then, this time that you're spending, which is a day setting up, it honestly spreads out through a week of time. Right. Whereas if you're doing a really small structure, which, I guess is something that our system has the ability to do, doing it with a bigger system, you start kind of seeing that let's say, that advantage that our system has on being like rapidly deployed. So it's very like a application focus. And at the end of the day, it's like, being able to set up the printer one time and then not having to reposition it, that's a huge plus. That's a pain from us. Nice. Okay. Next question on this same topic on the printers. It doesn't make sense for universities to focus on small scale printers and to have these in their testing facilities in very controlled environment, working with, maybe conditions that are not reflective of on-field conditions. And so how do we ensure academic research aligns with the realities of large scale 3D printing, specifically on site?
Yeah, so
I'm catching beef.
yeah, so with this one, I think the power in our research has been the partnership, is because Ben would come up with ideas and developments, and then we would go to LX and run it through their system. It was a very unique partnership in that way because they would take the time to allow us to do that. And I think there's a lot of usefulness in that, translating very directly the lab testing, as you said, in a perfectly controlled environment into a field application, through a printer that was many times the size of what we have in the lab. And so there is value in that. But I would also argue there's a lot of value in the lab scale testing too, to do proof of concept, to do, I really love the design optimization you're doing with the print forms, because that's, the first step in getting it into the field and at the full scale. And so I don't know if you want to add.
Did you guys feel, and both of you that are working in academics, is that that the correlation, that there was like useful correlations that kind of, once you understand how a lab scale 3D printer kind of like correlates to a large scale 3D printer, that those correlations are able to be generalized for a broad set of work? Or are you kind of like reworking stuff from the beginning all the time? You're not, yeah.
Depends. So at the university level, you may not have enough budget to buy larger printers. The material we develop in our research, we use the benchtop printer first. We learn from it, we adjust the mix, and once we have the printer in place, we're able to transfer that quickly to the system instead of just waiting. One thing we have a discussion before with academia is, I think we are guilty of trying to find perfection sometimes, or new ideas that's not applicable to actual real life. There is funding sources different from fundamental to practice, and I think there is a lot of research going on that of interest to practice, but also research that could actually hinder the quality and the practicality of the technology. So I think if I have advice for academia, is just find the practicality first and improve upon it. And I really like, the concept you have with large aggregates and try to minimize the cement content. And so, yeah.
Yeah, I like that. It's like find yourself an industry partner that can at least validate the need for whatever you're researching. That's a fair suggestion.
Yeah, the biggest thing for us is who's paying for it and what do they want to know. So for us, that was starting with a new printing system, starting with stuff that's already available, commercial off the shelf, and finding out why that's not going to be applicable for what we're doing, right? So it was, and I don't like to like name drop companies, but we're printing with SIKA mix, we're printing with a My multi-mix pump, and right away they're like, no, that's not what we're talking about. Get outside, dig up dirt, start printing. So that meant, how are we going to mix it? How are we going to pump it? How are we going to process it? How are we going to do all these things that we're going to need to do that they're interested in, my customer, right? So that was kind of how it unfolded. So it was almost two-part. We had, field construction people doing things outside, just working with stuff and what can we do there. And then we have people in the lab working on, I'll say, like the more scientific method behind all that, right? And we oftentimes have things that happen in the field that start working and they're like, why is that working? That doesn't make sense. So we've got to kind of start reverse back on that of like, what did you do? Give me exactly what you did. Write it down. And sometimes we find some of our most progress that way just by getting out there and getting hands dirty, right?
I like that. Open the floor to anyone that has questions about 3D printers, the machines themselves. We're going to transition into the pump system, but before we do that, I wanted to open the floor. Yes, sir. Do you want to come in to grab the microphone? Oh my God, super loud.
Got a real rally going out there.
Hello everyone, I'm Moin. I want to ask a question about the pump you're using in industry. What is the type of pump you're using? It's auger based or ring and piston based? And how often do you experience clog in your pump and in your hose? I want to know some detailed information about your pump. Is this commercial available or you developed it by yourself? And what problems do you have with your pump? How did you fix it? And what problems you have now?
I can speak about the MTech is the one that I have, and I also have experience using a little bit the My pump. So MTech and MIA, My, are the two I would say like most popular brands of concrete 3D printing mix and pumping systems. And so those take the premix, mix with water, and you get your material. Both of those are progressive cavity pumps. So they're not dual piston pump. The reason why using dual piston pump is really hard is because then you get that pulsating motion of the dual piston pump, which is hard to work with. Now, I'm excited for his comment in there, but on the limitations of a progressive cavity pump, it's its inability to work with larger aggregates, right? You're typically, yes, progressive cavity is auger based. And so you're limited at roughly like 5 millimeters, which is right from like sand. It's sand. And so like smaller aggregates means more binder, means more cement. It means that you're also kind of just not running concrete, really, it's mortar. And so we are printing with mortar, and that's what most, I would say, commercial 3D printing operations are using, except the few like we have, with LX and with Jim's Acme Tech that they're doing on-site mixing and they're able to get through it. But Jim, please, got some cool.
Yeah, talking about LX, because in the lab we have a progressive cavity pump that is about worthless because it's the same thing. It's too small of aggregate. If I'm going to use that small of aggregate, then I just go to my other extrusion systems. With LX, they just have a truck-based dual piston pump that pumps it all the way up, and then it flows down to the head with the cobot printer, where then the cobot printer has a screw type auger to do the final extrusion. And so the pump then is only the delivery system to the extrusion head, which I feel has a lot of nice control, especially when you're talking about, is it 60, 80 feet of basically pump hose that the material has to travel through before it gets to that extrusion nozzle.
Yeah. So they hit on the two kinds, right, that are mostly used out there. I think some people have tried peristaltic as well, and you get the same kind of, pulsating bead buildup as you do with dual piston, kind of unmodified, right? So I think really Cobod was probably the first one to go dual piston. And the way they handled that was like, it's like almost like a hopper. So the material's pumped almost into a hopper. We looked at trying to do that. The downside for us is it's too heavy. For the system that we have, it's a large print head. I don't know the exact weight. I think it's out on the internet, but it's several hundred pounds, right? And it's too much for what we were trying to do. So we had to figure out, we knew we needed a piston pump because, as others have kind of stated, the progressive cavities, we've gotten up to 8 millimeter particles working through there, but it really starts destroying the components. You could get about 4 to 8 hours of printing on it, depending on the angularity of your coarser aggregate. I won't even call it coarse aggregate, but coarser aggregate. And if you're using like a pea gravel, maybe towards the 8. If you're using something more angular, you might get closer to 2.
And just for context, normal progressive cavity pump rotor stators last for like 300 hours, you know, so on my end, we're using sand. So you're going from 300 hours to like 3 hours or 4 hours, you know, as you're mentioning. So you're like cutting down your life of your thing in like 100th.
Go ahead.
The power-based pump, you mentioned that you don't have any drinkability problem and continuously you can drink. But with the piston pump, you provide an extruder and you fix this problem of
Pulsating.
pump. But one question in my head now is there any bleeding or segregation problem with piston pump you experience?
Not that we've really experienced, no. It really depends on your mix, though. That's really a material problem, kind of like Jacob was just talking about before. If you've got the right mix dialed in, which can be a little bit challenging, but if you get the right mix dialed in, you're not really seeing those problems. But as far as clogging goes, like for us, we run, the pump we have has 4-inch cylinders. We do reduce down to a 2-inch hose because running 4-inch hose is somewhat unmanageable for what we're trying to do. It's just very heavy, pounds per foot, right? You could do the math on that. It adds up in a hurry. So we run with 2-inch. So we try and keep our coarser aggregate to 1/2 inch minus nominal. Some larger particles do get in there. If they get too big, the first place we look for the clog is usually where it occurs, and it's right at that reducer. So we back the pressure off, we pop the hose off, clear the rock or whatever debris out, hook it back up, and you're usually going again in, inside of a minute.
Cool. 2 questions. Yes.
Just wondering, and also the larger scale configuration. So I'm just curious about this possibility or architecture and engineers, like they always leave parallel and never like every direction.
So my personal thought, outside of Acme Tech, because we're really mostly interested in strength and utility of things. So there's not a huge architectural play to be made for me specifically there. But personally, having interest in this, I think there should be a lot of collaboration there.
So I work with an architecture professor who does 3D printing. She is looking more at 3D printing basically concrete molds, and I'm 3D printing concrete. And so she and I actually basically swap classes every semester or every fall, where I go and talk to her class. Her class comes and talks to me. I've advised their architecture projects. I'm not an architect. I've never done architecture. So I'm like way fish out of water in that situation. But I agree. I think there's a lot of opportunity on the architecture side to take advantage and leverage the flexibility of 3D printed concrete. And I think we'll get there when we figure out just how to do the printing part of it.
Mm-hmm. Yeah, I almost would say to that I completely agree to that last point, that it's like it almost seems like we're still figuring out the engineering kinks and like how to make this work in the first place. And like it is advancing quite quickly. So for architecture to keep up with it, I think it's going to be a little bit challenging because there's still a lot of engineering work that needs to be done before there's like a good set of guidelines that can be provided to an architect. It's like, okay, work with these parameters so that we can print this thing. Right? It's like I feel like right now the bigger parameters like, okay, you can do curves on X and Y axis, pretty much. You know what I mean? Like, but then when it comes to overhangs, for example, the work that Islam is doing, it's something that is like not present at all in the commercial space. Like, no one is doing overhangs on concrete, really, unless. Yeah, exactly. So it's exciting, but it seems that it is a bridge that will likely be crossed once the engineering part is a little bit more figured out. But I mean, good. I want there to be more collaboration.
One thing to add, one low-hanging fruit is landscaping. You can use 3D printing of concrete for a lot of nice landscaping projects and outdoor furnitures and other stuff. In fact, I'm collaborating with a couple of faculty from different universities on some different designs and using Grasshopper and other stuff, good stuff. Yes, we need to scale it first in practice, and after that, come up with geometry that is not easy to do. I think curved walls and other stuff on homes that is tough to do with forming will be good collaboration too.
Yeah. I would also just add that I feel like architecture drives demand because the architects are ultimately what implant ideas in people's head about what their house could look like. And so if 3D printing is not in the architect's mind, then they're not pushing it to the client. And if the client is not asking for it, then there's going to be less investment in it. And so there is this need for architecture to understand what 3D printing could be, in the hopes of the client thinking, I want my house to be 3D printed. And for me, a concrete 3D printing company to have an unfair advantage in securing that project, right? Because I do say that from a commercial standpoint, my biggest issue is that the projects that come to us were not designed for 3D printing in the first place. And then they're like, well, can you do this? We're like, yeah, but you have to change like a lot, So yeah, that's another point. Appreciate the question. Okay, I think that through the conversation, maybe some of the comments from the gentleman, we kind of started talking about pumping, and so I want to wrap up this pump conversation by just basically asking everyone: do we think that 3D printing can become competitive without on-site mixing? Like the MTech and the My Pump, they use premix. And what we're paying for materials like $600 a ton, $650 a ton, and what you're paying for traditional concrete, like a quickcrete, pallet, is like $200 a ton. And so, is concrete 3D printing going to be viable? Without switching to on-site mixing, do you guys see that even as a remote possibility?
No.
Cool.
No, in all seriousness, probably not, right? It needs to get down towards ready mix prices. You do get some reduction in labor through 3D printing, but it's not a ton. You still have people out there doing things. They're not working as hard, which is great, and they can probably work, longer. I come from the trades space as well, and when people reach a certain age, they're tired. Right, and that age is different for everybody, but they're tired. So I think people can stay employed longer doing this, and I think you're not going to reduce like a bunch of people, but you are going to reduce the amount of physical labor that those people are doing.
Mm-hmm. Cool. We are in agreement. Yeah, I mean, as an on-site mixing, let's say operation, it's going to maybe cost you $200,000 to $400,000. And if it's saving you $300 a ton of material by decreasing your cost from maybe like 600 to 300, which 300 is still a little high for concrete, it takes about 700 tons of material to break even. And if you translate that to homes, specifically the homes that I was showing, that's about 30 of those homes. And so I just want to kind of put that out there as a figure. It's like, us as a company, we'd be looking to secure a big enough project like that so that we can make that investment. And so I just want to kind of put that in people's head that it's like, this is the scale that we're playing to get to the cost that we're aiming for. Right? So next part is I want to go to the larger aggregate advantage. We actually already kind of went through this part. And so to wrap up here, I just wanted to ask, is using larger aggregate a must, right? And do we have a good understanding of the amount of cement that we can reduce? Let's say, I would love like a rough number, but it's like, can we cut our cement by, content or binder content by half by increasing our aggregate by double? Is that like, is there a rule of thumb that you guys have seen?
I don't think there's a rule of thumb, and it's really part of the problem is equipment. So what is pumpable by a progressive cavity pump and what is pumpable currently by a dual piston pump are two different numbers. So there's like a minimum, what we have found is there's like a minimum, and since I'm using soil, right, I'm going to call it fines content. So silt plus clay plus cement, that will, when you get below 30-ish% of that, it just, the material starts packing at the end of the rotor stator and just kind of deadheads, and it just doesn't pump, period. That you don't have that same problem with the dual piston pump, but you do need to coat particles with paste in order for them to stick together. So there's also, you can get below the 30% mark, closer to where ready mix, numbers are, but you can't, there is a certain threshold that you're not going to be able to get below with cement, because you need to coat the particles. And, I think we've all seen that, experiment in Soils 101 where, you dump out a jar of gravel, you dump out a jar of sand, you dump out a jar of clay, and how much surface area is involved in that, right? So it's quite obvious that the optimal content of larger aggregate you can put in there will definitely drive down, paste content needed, right?
Yeah, I agree. And I think, for this to be commercially viable, I do feel that incorporation of coarse aggregate is a necessity. Not everybody is there yet, and that's fine. But that should be the ultimate goal. There's a reason we use coarse aggregate and all the rest of the concrete, and this should include that. As I mentioned, or somebody mentioned, a lot of the layer thicknesses we're seeing in the commercial printing are pretty small, where incorporating 3/4 inch aggregate, well, that's their layer height. That's not really practical. So if we can get back up to 3, 4, Nathan's gone up to 7.5 inches in a layer height, all of a sudden, yeah, that makes complete sense that we should be including coarse aggregate. It's going to optimize our aggregate system, start to bring down the paste contents that we see, and ultimately just be a better structure.
Nice. Appreciate the comments. And you kind of, let's say, foreshadow this other aspect that I feel like it's worth sharing. When we were doing our testing, we noticed that, we're working with a commercial material that has roughly a layer time of 3 minutes. And it didn't matter if we were having programming our Z step-up height, so our layer height, to be 15 millimeters or to be 25 millimeters, which is almost double. We were seeing the same layer time, roughly. And so the layer height didn't proportionally increase, the layer time, as I would normally think that, because you're putting more material, you have to wait more time for the material to cure. And so there does seem to be this weird thing where, even though your layers are growing, you still have to wait a similar amount of time. Which then, kind of to what your point you were saying, Jacob, it's almost like now that layer height is taller, you're effectively printing faster. Right? So, when we increase from 15 millimeters to 25 millimeters, we're literally going almost like twice as fast. And so what are the things needed to get above 25 millimeters? And that's where I think, honestly, the nozzles and the work in that field starts becoming very relevant. The traditional shape of a nozzle tends to point downward, whereas layers that are thicker, than an inch, in height start having a nozzle that kind of looks almost like an L shape. And so being able to play with nozzles allows you to then have taller layers, which then increases your efficiency drastically, since you're not increasing your layer time. And so I just want to kind of share this little piece of information that I was able to gather while we were doing our testing. Any questions from kind of these points specifically, or points?
I'm going to push back on that.
Mhm.
It's not the nozzle design that's controlling that. It's the rheology of the material. And so it all comes back to rheology, and that's why we focus so much time and energy on that. Because once the material becomes stable, then it doesn't, that allows you to go to the bigger nozzles that allow for those taller layer building operations.
Gotcha. So it goes material, and then you can optimize the nozzle. But if you can't
Right.
optimize the nozzle, if you don't have the right material.
Right.
Fair. Awesome. So I want to talk a little bit about, on this idea of optimizing and making operations more efficient, the importance of grouping. And so grouping is the idea that you can print multiple objects at the same time. So you print a certain amount of layers in the first object, and you move towards the second object, and you print the same amount of layers, and you can go back to the first object, and then continue alternating with the idea of, again, extending your layer time. And so extending layer time does have advantages, because the longer your layer time, the less you need accelerants, the less sort of like additive packed your mix is going to be. And so the more that you can, again, rely on not using or not be running the print super quickly, you also reduce your chance of clogging. And so I do want to put it out there that grouping kind of feeds as well to kind of this narrative that in order for operations to be more efficient, you can effectively increase your layer time by grouping, among other things. And so, Jim, how often do you group layers, and do you have a good rule of thumb? It's like, if something is less, for us, is something that is less than roughly like 15 feet of linear length. If a layer is less than 15 feet of linear length, we are going to be printing more than one of the object.
Yeah. So our objects are not, linear generally, and housing and that kind of thing, right? So they're, like you saw them before, right? They're, bridging pieces and obstacles and smaller stuff. So in order to get the layer time that's optimal for the material we mix up, that's exactly what we do. We print 4 things at a time, 5 things at a time, whatever. That's exactly how we kind of obtain that optimal layer time. But, layer time's a double-edged sword, right? Your material has to stay open long enough where you get good bonding to the next layer, which our things are generally small. We don't have that kind of a problem. But I could see how on larger prints, you need to think that through, where you need to come back around to that point to make sure you get some good bonding between those layers. And I think there's still like work to be done on exactly what's the right QC test in the field when these things are happening, probably. And there's a lot of work to be done in standardizing tests and stuff in this whole 3D printing concrete industry yet. There's really no standards almost right now. Things are almost individually approved for the most part. I think there's a lot of people working that way, but there's not a great consensus yet on this is the way we're all going to do it. This is the way we're all going to make a compression sample. This is the way we're all going to, do whatever. I'd be interested to hear just like how others are doing that. We try to take up the most representative of, we print a block, a waist shape right next to it when we print 4 things, and we core samples out of that, and that's what we check. I think that's the best way, but others may have a different opinion on that. But as far as layer time goes, it's definitely a consideration with your material you got to make. Do you guys have a QC sample that you guys are using for strength testing?
Nathan doesn't, because all the times we've worked with the mix, we verify it through standard samples. We haven't done any coring out of that. The wall testing that I'm working on right now, that they actually sent us additional printed walls that we're going to core out of and do the testing of the in situ material. I'm assuming they retained material that they've made standard samples. I think you do need to do some type of coring operation. Now, coming to an agreement on does the core need to be interlayer or intralayer? We can probably fight about that a little bit. Talking about layer timing, usually I don't think that's as big of a discussion as how are we taking the cores, where are we taking the cores, and then we can get into a whole other discussion about how do we cure a wall versus cure like a cube section where we're taking and then we can really get into a long conversation.
Typically core. Or
Okay, so
Yeah, my interest there is, I mean, we do, as we're doing research on this, we do multiple ways, right? We're making cubes when that's appropriate, when we have, mostly fine aggregates. We're making, 4-inch cylinders, casting them when we have coarser aggregate in the material. We're coring things, we're doing it all and looking at the numbers side by side. And I'll just say, when you read packages, my first question is, how did they test that sample? Because the numbers can vary widely.
and especially when you're dealing with on-site mixing, right? I mean, like if if you're pre-blending, then you get a little bit better understanding of the QC. But if you're on-site mixing, then especially when you're dirt. Okay, so we're coming to the end of this presentation. I did want to. Oh, please.
So I want to ask about when you print on job site, how do you view that concrete? And another question is that I saw that you have printed like pipes and those kind of stuff. So how do you control the shrinkage on those? Or on, I think it was your slide that the guy was shirtless because it was very hot. So I assume in that temperature, you should get a lot of like shrinkage cracks, especially on the mortar. And on the slab, small bridge that you printed, how do you control the like freeze-thaw damages or like that?
Yeah, so long-term durability, like freeze thaw and other, things, environmental impacts, we have not really considered because, like I mentioned, expeditionary nature, year or two in service, right? I use black rebar, right, in my stuff. So we're not really considering long design lives for what we're doing right now. And that's because of the soil base of the thing. I mean, you don't want silt in your concrete, but we have to use that, right? Because that's what we have on the site. So for that use case, that's the way we've gone. But shrinkage cracking, that's something that we've seen since day one, right? So we kind of did a mini study on the side on how should we control that? Because if you just let it sit out in the air, it really depends on the print. If you do one of those big blocky dragon's teeth, it's not too bad. But if you're doing the wall sections, a lot of shrinkage cracking is what we saw. So we just air cure, ambient, whatever. And we looked at spray cure, both the like water-based and linseed oil type based spray cures, and then also just putting plastic over the top, right? Best performer that we found so far, plastic. Spray cure definitely helps. You get a lot less shrinkage cracking, but still a little bit. And I attributed that personally to you can't really coat all the faces, right? When you've got some of this lattice stuff going on and some of the prints that I saw, you can't really do it while you're printing because you'll get bad bond between layers, right? It'll impact that. And then once it's done, how do you get in every little nook and cranny and make sure you get that all covered, right? So plastic has been the most effective for us, and that's our recommendation to the people that we teach is that we cover it with plastic. You probably saw some of the pictures that we had plastic over some stuff, and then we were printing off over here. So that's how we handle it. We're still got some ongoing study going on in curing methods right now. Plan on putting a paper out about that hopefully in spring. But yeah, that's kind of what we've generally found. But a lot more numbers and data to back that up will come out.
Same plastic tarp works, but I haven't tested other things, so I don't know if there's a better alternative.
Our sections are too big for that, so like it just cracks. And that's where like mixed design optimization again is so critical to get the cement out, get the coarse aggregate in, and try your best to control it there. We're trying to print consistently and reliably, and then we can start to tackle some of these issues with shrinkage and a whole host of other things.
Yes, sir.
Yeah, one thing we do in our research is topology optimization, where you really try to print smaller beads, and this is like two times difficult shrinkage wise. So our lab specimen is not too large, so usually plastic can do a good job. But yeah, definitely, if you want to go for optimization and smaller beads and thinner beads for optimization, it's a double problem.
So you have more surface area?
Yeah.
Cool.
And rigidity of the layer itself, resisting the shrinkage.
Yes.
We have also found that we use polymer fibers, and that's helpful.
Yep. I agree.
When you get a big wall, for example, for a home or a warehouse, which type of shrinkage your preference? Covering in plastic or fogging?
Or what? Oh, we have just covered it with plastic tarp. We have not tried misting, but so far the plastic cover worked really well. Our mix does have a 0.5% of fibers on a weight basis, with roughly like 5% of it on a volume base, because it's just very not very dense. A plastic fiber. Well, go
Sections
ahead,
are too big. That's all I was going to say. Fogging is not practical. Tarping a wall, like the more recent stuff that has been printed is 25 feet tall and 30 something feet long. Once you get up above 10, 15 feet, having tarps covering it, and then you're also disturbing that top layer. So then when you come back the next day, then what's your bond going to look like? Since you basically use plastic to cover it, again, we're just dealing with it with jointing and kind of approaching it with that standpoint.
Yeah, the only one we haven't tried is probably dissipating spray cure yet, but it's on my list.
Any other questions? Fantastic. A round of applause to our participants.
Hey, well, at least I'll stick around if anybody wants to chat afterwards. I have some flyers on Acme Tech up here if you're interested as well. Thanks.